This is an advanced exercise. There are no tricks here. So pay very close attention. And if you understand this, you will be able to use this methodology to solve any other advanced circuit that looks vaguely similar to this. First of all, I'm going to write this circuit like this. I'll say that what if both of these diodes were off? What if this diode and this diode were off? Well, if these diodes were off, I would not have a closed circuit, alright? An off diode means that the device is an open circuit. So this circuit will be open, this circuit will be open. So I would have nothing but a resistor between the output and the inputs, and I would have no closed circuit, so there would be no current, so the output would be the same as the inputs. Right, no current, no voltage drop here. Alright, that was easy. Alright, now, what if D1 was on? Well, in that case, if I name this node N, I would say that in order for the diodes to be on, it would satisfy one condition. Vin minus Vn should be equal to Vd1 on. How much is Vn? Vn is Vb plus Vout plus Vout. Therefore, minus Vb minus Vout. Right? It's not just Vb, there is also voltage here. Alright. Now if I sharpen things like this, I would have a relationship between the input and the output of this from this equation. This says to me that in order for these diodes to be on barely, the input voltage must be equal to Vd1 on plus Vb plus whatever voltage is here. Alright? Now what if I forget about this diode and check when will this diode be on? Well, if I name this point A, for the diode to be on, I should have this relation. Vout minus Va must be equal to Vd2 on. Right? Now, if at the same time, okay, this is a mistake. If D1 is off, so if D1 is off and D2 is on, I would have a common current flowing from here to here, and I could write the circuit like this. Again, just a hypothesis, maybe D1 is on, alright? Let's say what happens if D1 is off and D2 is on. Well, in that case, the voltage here, the resistor and the current would satisfy this relation. Again, this is just Ohm's law. In that case, this equation would give me Vout is equal to Vd2 on plus R2 times I. Well, what if I want to see when D2 is barely on? So, if D2 is about to turn on, the current here must be very close to zero. This will not be exactly, but very, very close to zero. So, I just write a plus here, okay? In that case, Vout must be equal to Vd2 on because this is very close to zero. Well, if Vout is Vd2 on, and if the current is zero, then the input voltage will be equal to the output voltage, which would be equal to Vd2 on. Again, this is true because there is no current here, so there is no voltage drop here. or here, for that matter. Alright? What I understand here from this analysis is that, well, it seems to me that in the beginning, if the input voltage is very small, well, both of these diodes must be off. When the input voltage is large enough, by this value VD2 on, D2 will be on first. And D2 will be on up until one point where the input voltage will be equal to VD1 on plus VB plus some output voltage here. And then D1 will also be on. Alright? If you didn't understand, and if you have something that is not clear to you up until this point, watch this section of the video again. These are very advanced concepts, so it's important for you to understand what we are doing here and to understand in depth this methodology. Alright, now if D2 is on and D1 is off, the circuit reduces to this, okay? The diode is nothing but a battery. And we are here. The input is higher than VD2 on, and it's lower than some value, I don't know which, I don't mind here. And in that case, if I take Ohm's law for the resistor, it should be V in minus V out over I. Again, Ohm's law for R2. The voltage here, if you remember this point A, is equal to V out minus VD2 on because we enter a negative terminal. We come from a positive terminal. We enter a positive battery terminal. Therefore, we have V out minus VD2 on minus the voltage here, which is 0, over the total current I. And since this current is the same as this current, I can say that this is equal to this. And if I do the algebra, I get a relationship between the output and the input of this. This contains resistance values here, some type of resistance divider perhaps, alright, VD2 on and V in. Now this will hold up until D1 turns on. When will this happen? This will happen when this equation is satisfied from before. I just wrote it like this. So when the difference between this point and this point, so V in minus V out minus VB, alright, or we write like this or like this, is equal to VD1 on, then D1 will be on. And now if I take this equation and I plug it inside here for V out, I can find the input voltage that D1 turns on. This is the borderline situation in which D1 turns on and this equation no longer holds true. I plug this value for V out inside here and I get this result for the input voltage. Alright, obviously there is a mistake here. This is not minus, this is plus. VD1 on plus VB. Alright? Alright, now let me see what happens when both of these diodes are on. Well, this is a very simple case. For the input voltage higher than this value, again this is plus here. So when we reach that point, both of these diodes are on, Vin minus Vn must be equal to Vd1 on, therefore Vin minus Vout must be equal to Vd1 on plus Vb. So Vout is this in relation to Vin, same as Vin minus the voltage of the battery minus then again this is minus. So very briefly to sum up, for Vin lower than Vd2 on, both of the diodes are off and Vout is going to be equal to Vin. When Vin is equal to more or equal than Vd2 on and less than this, well, Vout then follows this equation. Now, for Vin larger than this, and this is the most effective way to solve these exercises. If you found this video helpful or you have any questions, write me down in the comments below and subscribe to the channel if you still haven't. Study well and take care.